In this video, we learn to evaluate integrals involving trig, specifically integrals involving powers of trig. There are 6 trig functions: sine, cosine, tangent, cotangent, secant, cosecant. So we have a power of each, basically, in the integrals we discuss in this video. Now, there are 6 different trigs. Now, not only are we going to talk about the integral of each individual power of trig, we'll talk about combination of powers, like a product of 2 powers or more, but mainly in like a 2. Still, when you talk about the combination of different trigs, powers of different trigs, that's a lot of like possibilities. This reason we want to categorize all different combinations and divide them into groups. The first group of integrals would be integral of a single power. For example, integral of tangent 2x to the 3rd power, or integral of cosine 5th power, such as a single power of tangent, power of sine, power of cosine alone. We'll discuss what to do for this kind of integral. Now, the second group of integrals we discuss are integrals involving powers of sine times power of cosine. For those integrals, we always need this trig identity for different reasons. Sine squared plus cosine squared equals 1. So again, in this group, it's a combination of power of sine, power of cosine. Those powers don't have to be positive integers. In some cases, they can be fraction, they can be negative, so we'll discuss in details later in this video. Third group of integrals contain combination of power of tangent, power of secant, or similarly, power of cotangent, power of cosecant. The way we treat this kind of combination will be same way we would treat this kind of combination. So we only discuss one of them, or the method we discuss would be applicable to both kind of combinations anyway, so we don't separately discuss them. And then also there are some other special trig integrals we'll discuss later in this video too. But primarily we're dealing with powers of trigs, combinations of power of trig. Now, before we get into much details, let's just have some general idea of how we approach integrals in each group. First group, single power. Now, if it's a single power, we can always use a formula. There is a table of integrals in the book. You can find in the book that's usually depending on the version of the book. In the 7th edition, it's the page opposed to the inside cover. But any calculus book, you're going to find this table. Anyway, so for single integrals, we basically use a formula. Now, even the formulas, it's useful to know that depends on the order. If the order is third power or less, there's a what I call straightforward formula. So if it's a first power, second power, or third power, up to third power, there's a formula we can apply to get the answer right away. No more work. So I consider them as a direct formula. For example, this formula is a little hard to see, but if you find your table in your book, it says secant square, so you find the answer right there. No more integration. That's what I call direct formula. You can check further third power, you get the answer right away. Any third power, you get the answer right away. And there's a reduction formula too we can apply. That's for powers greater than or equal to 4, like a fifth. For this kind of powers, there are what I called reduction formulas. My table is number 33 to 38. 6 of them for each kind of power. Power of a sine, power of cosine, power of tangent, cotangent, secant, cosecant, and so on. So these formulas are called the reduction formula. They're not what I call direct formula, because each time we apply those formula, we don't get the final answer right away. On the right hand side, there's a new formula. There's a new integral, I'm sorry. But the power is reduced. The power is always reduced by 2, from n to n minus 1. Every formula you can see. And the power of a cosine, you have n minus 2 on this side. So power is always reduced, which is better. It's a simpler power, and then we see what we have to do here. Okay. So if you apply any of those 6 reduction formulas, there's more work to be done. By the way, these reduction formulas can be proven by doing integrating by parts. We're not going to get into the proof of this formula. Just the integrals in this group, single power, any single power. Either we apply direct formula or apply reduction formula. Now, for the combination of a power of sine and cosine, there are 2 types of integrals that we can integrate. The others we cannot. So let's just see the 2 cases we can. First case is if m or n is odd integer. It's power of sine or power of cosine. If one of them is odd, we can do it through some substitution, which we'll talk in details later in this video. There's another case when m or n both even. We can evaluate the integral too. So those are only 2 cases we can evaluate. There are other cases we cannot. For example, if one is even, the other is a fraction, we cannot. Well, actually, in this case, if one of them is odd, the other can be anything. So there's no restriction, no condition on the other guy. But anyway, so if we have a combination of a power of sine and power of cosine, those are the 2 cases that we can do. Now, in group number 3, well, the combination is between power of tangent, power of secant, or power of cotangent, power of cosecant. We need those trig identities. 3 cases we can do. First case, M odd. Second case called 3b, N even. Third case, M even, N odd. It's like the opposite of first 2 cases. Again, there are other cases that we cannot do. So these are the 3 we can do. Alright, so let's get into each group and each different cases to see how we approach different kind of trig integral. First, single powers. So just one power alone, power of sine, power of cosine, and so on. Let's see one example. Here is a third power of sine, and remember the power is 3. We can apply direct formula. Now, in all those formulas, the variable, whatever power, is a variable alone. So in this integral, it's a 4 times variable. We have to do a substitution, take care of this 4 first. So say u equal to 4x, simple substitution. du equal to 4 times dx, or dx equal to 1/4 du. Plug in. Turn this into a plain variable inside trig, just u, not 1 times, not 4 times u or 2 times u. Now we're ready to apply direct formula. So you go through your table of integrals, find the third power of sine. Here, number 24. So according to the formula, it's a direct formula. You can see we get the answer right away. So copy down the 1/4 from the formula. It's a negative 1/3 2 plus sine square u times cosine u plus c. No more integration. So direct formula. Then multiply 1/4 through. Oh yeah, you get this x back. 4x back in for u. And 1/4 times c is just arbitrary constant, so still called c. Alright, single power. So formula method, okay? But then again, if you see 3x, 5 theta, 2t, you need to do a simple substitution first. Let's see another single power. This time the power is more than 3. So we're going to still use formula, but we're going to use reduction formula. Power of tangent. So okay, go by the list. It's 35. Alright, so we don't need to do any substitution here because this is a variable by itself, plain variable. Formula number 35 says nth power of tangent is a 1 over n minus 1, so it's a 4 minus 1. Tangent n minus 1, that's a 3. 4 minus 1 is 3. x minus tangent n minus 2. 4 minus 2 is 2 x dx. Alright, so you see this is not a direct formula, rather reduction. The power is reduced, fourth power to second power. Well, let's see integral of a second power. Number 22. So integral of tangent square is tangent u minus u, or tangent x minus x. Tangent x minus x plus c. Done. Okay, so for integrals in this group, single power, any trig, power of any trig, power of sine, power of cosine, power of tangent, power of cotangent, so on. We apply a formula. Only difference is if the power is less than or equal to 3, there's direct formula. If it's more than 3, there's a reduction formula. No matter what formula, if it's not plain variable inside trig, 4x or 2 theta or 5 alpha, you have to do a simple substitution first. Now let's see integrals in second group of power of sine and power of cosine. Remember the two cases. One of the power is odd, or both powers are even. Alright, so let's see what we do. Second group, first case. Now in this case we expect to introduce some substitution to turn everything to powers. So we basically just integrate power. How it works out is this. Now there's power of sine, power of cosine. Suppose power of cosine is odd. Okay, let's just say to get some idea, we see example. Suppose power of a cosine is odd. Say n is odd. So what we do is this. We would get a copy of a cosine, put in the back. Remember, see, we start with the n part, right? Now I get a copy of cosine, put it back here. Now the role this copy plays is like a supporting factor. So I'm thinking about a substitution, u equal to something. For that to work, I need cosine. You can quickly think a substitution would be u equal to sine, right? If u equal to sine, if differentiate, you get the cosine dx. That's exactly the combination I have here. So really, if I have cosine next to dx, I want to try this substitution. For this to work, of course, everything else must be turned to sine. Therefore u. Well, you can see whether this can work out. If we're going to plug in u for sine, this will become power of u. So that can be taken care of. And what about this guy? This power? Well, this power now is perfect because we assumed n is odd. Therefore n minus 1 is even. N minus 1 is even, so we're talking about second power, fourth power, sixth power, and so on, right? Now according to the trig identity, any even power of a cosine can be turned to sine. Cosine square, well, it's obvious. So 1 minus a sine square. But if it's a fourth power, we just square both sides. So you can see, it's a simple algebra. Any even power of a cosine can be turned to sine only. So that's how we take care of this guy. Alright, so it's not just how it would work out in this case. Other cases we're going to discuss later on. Some cases we put some trig in the back next to dx. It's because we'll be thinking about some substitution to use. Alright, so let's see example here. So this case again, one of the power is odd. Now this integral, let's check. Third power, fourth power. So this part is odd. Okay. Then we get a copy of sine this time. Third power. So let's take a copy away from it. Second power. Cosine. We're not going to do anything about it for now. Put sine phi in the back. Phi is integration variable. What's important here is we got the sine next to the differential, the variable. So we are thinking about a substitution, and the sine phi would be the supporting factor needed. What is substitution? Very simple. Differentiation will tell us gotta be cosine, because if you differentiate, this is going to give us like a negative sine phi d phi, so that's pretty much like that. Then of course we would try to turn everything here to cosine, thus u. So let's see if it's going to work out. Okay, so well, with this substitution, that's the first. The du equals negative sine phi d phi. So that says sine phi d phi equal to negative du. Okay, so this part becomes negative du, and part of a cosine, well, becomes part of u, right? What about part of sine? Well, look, we start with the odd power. With the copy taken away, becomes even power. Even power of sine, according to the symmetric identity, we can see sine square equal to 1 minus cosine square. Therefore, any even power of sine can be turned to cosine. In this case, cosine is u, so it's 1 over u squared. So sine squared equal to 1 minus u squared. That's exactly what we have. Even any other even power, we can get u in the new integral. And look, we got an integral in u, and you'll see it's a very simple integral. To evaluate this integral, pull out the negative and multiply the fourth part through. Very simple integral. Well, what's the integral of? It's 1/5 u to the 5th power, 1/7 u to the 7th power plus c. Bring back the cosine. Cosine phi 5th power, cosine phi 7th power plus c. Alright, so integrals in this case, when m or n is odd, we can get a copy in the back. We use it as a supporting factor to try some substitution. Now, second case. In this integral, both powers are odd. Well, this time we cannot expect like a u equal to sine or u equal to cosine kind of substitution to work out. So what we can do is to rely on the substitution to turn everything to sine or everything cosine, because you can see here sine square equal to 1 minus cosine square, cosine square to 1 minus sine square, depending on situation. In theory, either way would work out. In practice, maybe one way is better than another. Let's see. Okay, let's see this example. Now we have square of sine 3 alpha, square of a cosine 3 alpha. Alpha is an integration variable. Both are even. Now both are second power, so really there's no difference at all whether you want to have all cosine or all sine. Now first of all, it's a 3 alpha. Let's take care of this, because in this case there's no hope for u equal to sine or u equal to cosine, that kind of substitution. We need to take care of the 3 first. Okay, we'll do a substitution. U equal to 3 alpha, simple. We've done this a lot of times. It become 1/3 sine square u cosine square u du. And go here. So okay, both are even. Today there's really no difference whatsoever which way we do it. Get all in sine, all in cosine. So let's just solve for sine square and then plug in. So we can plug in 1 minus cosine square for sine. Right? Now, well, two things. One, you're not going to think, we got a cosine here, we got a cosine here, we have a cosine everywhere. Can we try u equal to cosine? No, because for that to work, we would have to have another copy of sine here, right? Supporting vector, okay, which we don't have. If we had that, well, it would be like a 3rd power here, right? That would be the case. The other case we already discussed. Anyway, so you have to be very careful. Just because you see cosine everywhere, you want to try substitution, you have to worry about the du. Without supporting factor, this du will not turn to differential of whatever new variable you would want to introduce. Another thing is the integrand here is a product. You're not going to try to directly see how to integrate this, how to integrate this, right? So the right way to continue is to multiply this through. So you have 2 integrals, basically 2 powers. Separately, it's a single power. It's a single power. It's a square, it's a 4th power. Well, actually, we now have sort of a group 1 kind of integral. Group 1 integral, remember, formula. Okay, so let's see. Really, this is just second power. This is the 4th power. For second power, there's direct formula. 4th power, there's reduction formula, and we talk about that. Now, this kind of integral, remember, when you do the reduction formula, right? From the 4th power, we'll end up with another second power. So we'll have to worry about the second power after we use a reduction formula. For this reason, I'm not going to worry about this second power right now. Okay, I wait till I get another second power and combine this with the new second power and do it one time. Okay, so the time being, I'm just copy down the first guy, leave it alone, and then well, let me actually just write that 1/3 through. Oh wait, that's u. Okay, so let's see what we have from this. Of course, reduction formula, because it's fourth power. Go through the list. It's the reduction is inversion. Cosine formula number 34 says this equals 1 over n. N is 4. Cosine n minus 1, 4 minus 1. Sine u plus n minus 1, so 3 over n. Cosine n minus 2, that's now 2. Reduction formula. Okay? Reduce the power from fourth power to second power. You see here, that's another integral of square of cosine, like that. So we'll combine and then apply whatever formula appropriate. Multiply this through, negative 12. Three over, oh, 3 cancel out, it's 1 over 4. Okay, now combine the coefficients of the same integral. This is an integral of cosine square. This is an integral of cosine square. Combine them. 1/3 minus 1/4 is 1 over 12. So this way, we only deal with integral of cosine once. How do we do it? Formula. Square of cosine. Here, number 21. Square of cosine. According to formula, it's 1/2 u plus 1/4 sine 2u minus 1/12. Let's just copy this down. We're done integration, so let's put the c here. Constant of integration. And finally, get the 3 alpha back in for u. 3 alpha, 6 alpha, 3 alpha, 3 alpha plus c. Alright, so this is how we evaluate integral that belongs to this group 2. In the second case, actually, when both powers are even. Turn everything to sine cosine. Now, let's see group of 3 integrals. Combination of power of tangent, power of secant, or power of cotangent, power of cosecant. They're done similarly. 3 cases. So let's start with the first case. In this case, what we do is to get a copy of tangent to get some idea before we work on example. M is odd. We're going to get a copy of tangent in the back. Also copy of secant in the back. Alright, our intention is to use tangent x times secant x as a supporting factor for some substitution to work. So when you think about this, the substitution we really want to try be u equal to secant, right? Because if you do differential on both sides, derivative of secant becomes tangent secant dx. Then of course we hope everything else will be turned to secant or u. Well, this is already secant, so that becomes a power of u, and the tangent, well, let's check. M is assumed to be odd, so m minus 1 will be even. With the even power of tangent according to the trig identity, we can turn everything into secant. That's how it's going to work out. Alright? So let's see this example. We got cotangent raised to the power and the cosecant raised to the power in the denominator. Alright? Let's first write it in this sort of a standard form. Okay? It's better to check this way. Now, second power on the bottom, you would turn to negative. Okay, so now we have exact, kind of power of a cotangent times the power of a cosecant. That's this. But how we classify, the same, whether you have a combination of a tangent secant or cotangent secant. We all go by power of the first one, power of the second one. Power of the first one called m, power of the second one called n. So let's see, power of cotangent is odd, m is odd. Okay, m is odd, we get a copy of cotangent, copy of cosecant back here. Now it's negative 2, so if we get a copy from it, then subtract 1 from it, right? So this is important. Got a cotangent, the cosecant together serve as a supporting factor. So if you remember simple differentiation formula, we want to really try cosecant 2x. So there's some substitution we can do. Now, if we can do substitution, we don't need to worry about the 2x. Like I say, should we try u equal to 2x first? Take care of it? No, because there is some substitution we have to do anyway. The 2x can be taken care of at the same time, the same substitution. Alright, so before we continue, let's check again, make sure we understand what's going on. Got the power of a cotangent, power of a cosecant. That's odd, so it's first case. First case, we get a copy of each, basically, put it back. So in this case, get a copy of cotangent, copy of cosecant. Then we'll try the substitution. Let's see how this is going to work out. So do the differential, du equal to chain rule, so negative cotangent 2x cosecant 2x dx. See the combination here? So the combination equals negative half du, this part. With the power, of course, directly becomes u to negative second power. The cotangent square, according to the identity, cotangent square equal to cosecant square minus 1. Subtract, say with the 2x in place. 1 from both sides, you have cosecant 2x minus 1. So cotangent square equal to cosecant square minus 1. The cosecant is u, so it's a u squared minus 1. Alright, this again would always work out because that's, we start with odd, get a copy in the back, it becomes even. If it's even, you see here any even power of a cotangent can be turned to cosecant. If it was fourth power, we would square both sides, so we still have square of, like I say, u squared. Alright, so with this substitution, we got a very simple integral of power of u. Move the 1/2 to the front and multiply this through. Integral of u to the negative first power is like a 1 over u, so get a log u, and integral power is the power plus 1, power plus 1 plus c. Right, very simple integral. Cosecant 2x, so get the cosecant 2x back in the expression for u. Negative 3 plus 1 is negative 2, so it's positive 1/2 cosecant 2x second power negative plus c. Okay, so this is the first case of integrals in this group. Power of tangent or power of cotangent is odd. Now, second case, n is even. Still, power of tangent, power of second, or similarly, power of a cotangent, power of a cosecant. Anyway, the second power this time is even. Well, this case, what we do is to get 2 copies of secant. Use it as a supporting factor. If it's a combination of power of a cotangent, power of a cosecant, you would have 2 copies of a cosecant put it back. Now, it's obvious this time we'll be thinking about the tangent, because the derivative tangent will be secant squared. With this substitution, that becomes directly power of u, and this, remember, is still even because we start with the even. N even, n minus 2 is even. Even power of a secant can be turned to tangent or u, so we can see this would work out. Let's say example. Okay, well, we check the second power. That's even, so clearly it's a 3b. Actually, this is also 3a too, because the power here is odd, but we want to treat it as a 3b. So get a 2 copy. Alright, we want to try u equal to tangent theta, du equal to secant squared theta d theta. Okay, so well, this combination becomes exactly du, u equal to tangent, so that becomes u. Then there's a secant square. Secant square, according to our identity, tangent square plus 1, so be u square plus 1. Alright, works out nicely. So multiply through first, u to the third power, u du, then integrate 1/4 u to the fourth 1/2 u squared plus c. Very simple. Tangent comes back here. All right. Now this integral I mentioned, sure, is type 3b integral because it's even. It's also type 3a because it's r. Now, if you treat it as a 3a, you would get a copy of this, back a copy of that, and try u equal to secant, that kind of substitution. And you expect if everything works out just like previous example, you would have power of secant. So the answer will look like quite different. Here is the power of a tangent everywhere. Treat this as 3a. You're going to see power of a secant everywhere. Both are right. If you actually use this trig identity, you can turn one answer to the other. Alright? So when working with the integral object involving trigs, the answers can look quite different. So normal. Now, third case, this kind of combination, okay, power of tangent, power of secant, or power of cotangent, power of cosecant. Case 3c. N is even. No, I mean m is even. N is odd. M is even, so it's not 3a. N is odd, so it's not 3b. What do we do in this case? In this case, we're going to turn everything to secant, and then later on use formula. It's just one way. You cannot turn everything to tangent. You can only turn everything to secant because, well, this is even. Right? When it's even, we can use this identity to get the secant involved. And later on, we'll rely on direct formula or reduction formula. Because of that, if there's like a 2x, you have to do a substitution first, a simple substitution, u equal to 2x. If it's 3 theta, theta, you have to do u equal to 3 theta, that kind of substitution. Okay, so let's get right to the example. That's even, that's odd. So we're going to use a similar identity which says cotangent square equal to cosecant square minus 1. Alright, and then multiply through. Two single powers becomes group 1 integrals. Have third power, there's direct formula. Fifth power, there's a reduction formula. Now, again, with the reduction formula, we expect the third power, right, in the answer. So right now, we're not going to do anything with the third power. Okay, let me separate it first. Okay, leave this alone. Let's just see what we do with this guy. Fifth power of cosecant. No, that's direct. Cosine is here, 38. Okay, n equal to 5. So let's apply the formula. We're having negative 1 over n minus 1, 4. Cosecant n minus 2, so that's 3. Cotangent plus n minus 2, n minus 1, cosecant n minus 2. Alright, these two are from this integral reduction formula. And there's the integral that was there. You see, integral of a third power of cosecant and another. So we're going to combine these two and take it off at the same time. Okay, let's see. This is 3/4, -1, so combined coefficient is -4. For this, the third power, expect direct formula. Third power cosecant. Here, 29. First, we copy down the first term. Empire formula. Formula says -1/2 cosecant cotangent minus 1/2 log cosecant plus cotangent plus c. Right? So this is how we evaluate the integral in this case. 3c. First power is even, second power is odd. Turn everything to secant or everything to cosecant. And then use reduction formula, direct formula. Okay, so those are powers of trig or combinations power of a trig. Powers alone or combination power, combination of powers. Now in this group it's a sine with cosine. This group tangent with secant or cotangent with secant, right? There are other integrals. I call them mixed powers integrals. What I mean is have not necessarily sine with cosine or tangent with secant. May have power of a tangent with power of a cosine. Right? You expect power of sine, power of cosine, second group, and this third group. Now we say, what do we do with this? Right? It's like a crossover. Well, actually, there's no unique way to do it. Unlike we can classify this case, that case, this group, that group. Instead, if it's not in this kind of combination or this kind of combination, we turn everything to sine, cosine, because tangent is, for example, sine over cosine. Cosecant is 1 over sine. So any trig, tangent, cotangent, secant, cosecant, can be turned to sine, cosine. So we get just all sine, cosine, and see what to do from there. Let's see one example. Now, it doesn't even have to be just a product. Could be just anything. Any expression involving just different kind of trig. Let's see this example. Say we have tangent x plus a sine over secant, right? Giving a fraction. But the point is, what different trig involved? A sine that we normally see in group 2, there's a tangent, the secant, just crazy. It's a sum, it's a fraction. But then again, keep in mind, just turn everything to sine, cosine at any cost. So tangent is sine over cosine. That's sine, that's good, let's keep it. And then the bottom is 1 over cosine. Well, this is what I was talking about. Turn everything to sine, cosine, and go from here. This is a complex fraction. We say, for example, multiply everything by cosine, common denominator to simplify, right? So we multiply by cosine. We multiply by cosine. And see what we're going to have and decide what to do. So, well, actually, the bottom, if you multiply, it becomes 1, so it's not a fraction anymore. Cosine times this becomes sine. Cosine times sine is sine cosine. Alright? So, two integrals. Totally different integrals that we do differently. To separate them, for this one, there's a simple formula. And this one, we can actually do a substitution, or we say, hey, this is like group combination of a sine and cosine, right? That's like 2, 1, because it's odd. It's odd here too. Or we just simply, cosine is like a supporting factor. We're going to do u equal to sine. So once you get all sine, cosine, you get the idea what to do. U equal to sine, du equal to cosine x dx. So actually, it's a simple substitution. Cosine x dx is du. Half u squared plus c sine. Alright, it's just a simple example. When you get combination of different trigs in an expression, doesn't matter whether it's a product or division or sum or difference, just get everything in sine, cosine to see what can be done. Alright, finally, there's some special trig integrals that we want to talk about. They're very special. Those integrals, we need trig identity. Sine times sine, sine times cosine, cosine times cosine. So we're really talking about integration of product of two trig. Well, got to be between sine and cosine. Okay, cosine times cosine, or sine times sine, sine times cosine. Okay, so it's actually pretty simple. We just have to turn using appropriate identity product to separate the trigs, the integrate. Let's see through this example. Okay, I have a cosine times cosine. First, let's see the identity. Cosine times cosine. So half a minus b. This is a, this is b. So it's a cosine a minus b negative 2x plus cosine a plus b 2x plus 4x 6x dx. Okay, the half. So to the front, I have integral cosine negative 2x dx and cosine 6x dx. You see, start with the integral of a product of trig with the trig identity split this into two separate trig. So cosine alone, cosine alone. From here, well, actually, move the negative sign outside first. Oh, no, not negative sign. It's an even function, so we just drop the negative sign inside. From here, just a matter of a simple substitution. U equal to 2x, v equal to 6x, that kind of thing. So simple substitution. U equal to 2x here, for example, you work out very simple substitution. Comes 1/2 cosine u du, and here say v equal to 6x, 1/6 cosine v dv. And this is a sine u, this is sine v. Simple integration. Simple integration formula. 1/4 sine u is 2x, 1/12 sine v 6x. We don't need the parentheses. Plus. Alright, so we're talking about really special products of sine and cosine only. Sine times sine, sine times cosine, cosine times cosine. Now, the a and b got to be different. They cannot be the same. If they're the same, we would have a power, we would have a square here, right? So we would do it, like in previous cases. So it's assumed a is not equal to b. As a matter of fact, it's a squared not equal to c. If it's not true, we would already know what to do from previous discussion. Alright, so you may have a sine something times cosine something. You may have a sine times a sine, cosine times cosine. Just one of those three cases. Term product respectively to separate trig. Each one just simple substitution like this. Alright.